I'm excited to speak today. So we're going to be talking about using data and how that impacts the solutions and behavior of the solutions for parameterized polynomial systems, where data is the main input, and that's kind of, you can maybe use data and parameters synonymously here. So we're going to use the data as the parameter input here. And so what I'm going to start with today is a little bit of an introduction on what are parameterized polynomial systems, where this data would go, how that then looks in terms of the algebraic geometry, more theory of using homotopy continuation to solve these problems. And then I'll go into a little bit more details on how we use the data within these parameter homotopies for specific examples in computer vision and kinematics. And then another problem in like more synchronization, in the synchronization world, the Kuramoto model, to talk about how the data impacts our ability to solve the solutions, finding just real solution sets, which is what most applications care about, right? They don't care about complex solutions. And then also being able to analyze any behavior of the solutions. And you know, later I'll go into what all of that means. And then finally, I'll summarize. So the reason that we're talking about polynomial systems is, well, these are what are used in our algebraic geometry theory for many reasons, but many problems in math, science, engineering, you know, I listed 3 specific examples, but you can go into biology, chemistry, so chemical reaction networks. A lot of these can be formulated using a system of polynomial equations. But for all of these, they're dependent on a set of parameters. So if we look at this picture here, I don't know how many of you have any knowledge about computer vision, but this is one of the most famous problems in computer vision called the 5-point problem. And so there's a polynomial system that defines this problem here. And what we're trying to do is reconstruct some scene, some 3D scene that's out here. So these are points in a 3D world. So if you imagine, you know, you take something on your desk and you put like 5 stickies on it. And so from that data, you're trying to reconstruct whatever object you have these 5 stickies on, right? But our polynomial system solves for this relationship between the 2 cameras. And then there's some computer vision theory that allows you to map back to the 3D image. But what you'll notice here is that this 3D part has in these camera images 5 data points in this camera C, and then 5 more in C prime. And so we have 2 views of these 5 stickies on the 3D object. And that's our data. Those are our parameters for our polynomial system. So this image point data for this 3D object reconstruction will change the solution set for our polynomial system, where that solution set describes this matrix that relates the cameras, which makes sense, right? So if we have 2 different cameras, our parameters xi and yi will change, which will then change the essential matrix that relates the positions of these 2 cameras. So let's look at this with a more straightforward example than talking about this 5-point problem. And let's actually look at what the system looks like. And so let's look at this parameterized polynomial system given by f. So our variables are z, which are z1 and z2 here. So we have 2 variables and 2 parameters p, p1 and p2. And so what we want to be able to do is solve this system for any set of parameters p1 and p2. But maybe for this problem, that's not so bad, and you can do that given any input p1 and p2. But a lot of times when we have systems, and I'll show you one later today, it's not as intuitive or easy to find the solutions to this system inherently. And so what we do is we use homotopy continuation, which is a piece of algebraic geometry, to be able to find the solutions to this system. And so what this entails is to be able, we find a start system for our homotopy. And what that means is we find a similar related homotopy or related polynomial system that we know the solutions to. And the general method is to determine some polynomial system G, and this is our natural start system that I list here. So G of Z, and what we do is we just take, so each polynomial is just the variable raised to the degree of that polynomial in F. So the degree of the first polynomial is 2, so we take Z1 squared minus 1. And we know the solutions here are 1 and -1, right? And then the second polynomial is still of degree 2, even though it's, it's degree 1 in Z1 and degree 1 in Z2, but it's degree 2 overall in the variables. And so we take Z2 squared minus 1, and we again know that that's -1 and 1 as our solution set. And so then for G of Z, we know our total number of possible solutions for that system. And so then what we have is these two pieces here. So we have our G of Z, that's our start system. We know the solutions to it. Then we have our F of Z at P. Well, like I said before, right, the solutions to F of Z at P, they depend on what the P value is, right? And so what we have to do is we have to choose a generic base point parameter, so a P0 that we plug into, so we have F of Z at P0. And generic is just, if you choose a random point, right, we just don't want it to be singular, and so if you choose it randomly, the likelihood of hitting a singular point for that system is low. And so the algebraic geometry or homotopy continuation piece is we take the solutions that we know from G of Z, and we deform to the polynomial system defined by F of Z at P0 using a linear homotopy. And so then we're able to take our solutions that we knew at G of Z, and using that linear homotopy, we're given then the solutions of F of Z at P0. And so we do this using a path variable T, and we move our, some conventions are to move from T equals 0 to T equals 1. But our convention in like the Bertini group, where Bertini is a software that performs the homotopy continuation, among other things. But our convention is to start at T equals 1 and to move by using a step size to T equals 0. So we track along the path that direction. And so what does this look like? So we have, just like I mentioned before, we know our two solutions for each of these quadratics are 1 and -1. And so we take the possible combinations of these, and we're given these 4 solutions. And so we have 1, 1, 1, -1, -1, 1, and -1, -1. And these are not in any sort of required order. They're just labeled randomly, effectively. And so we start at T equals 1, our path variable, with these 4 solutions. And if we look back at our homotopy equation, right, at T equals 1, our F of Z at P0 term disappears, right, because this coefficient is 0. So our homotopy is only defined by the solutions at G of Z. And then as we change T, right, this becomes less than 1, and this component here becomes non-zero. And so essentially what we're doing is we're transitioning and deforming from these solutions, these 4 solutions along these paths, to eventually have the components only being the solutions at f of z at p0 when t equals 0. Because if we look back at our equation when t equals 0, there is no impact from our g of z, our initial start system. And then we have only an impact from our f of z at p0. So those are then the solutions of f of z at p0. And so this is kind of an image of, possible paths that connect, and then we get 4 solutions over here. Now, how do we move along these paths, right? So we use something called a predictor corrector method. And so what we do is so if P0 is our initial solution, like 1, 1 to our G of Z, we predict to extrapolate along this path to the next point using our homotopy equation, H of Z and T. And then we correct to refine back to the path, right? Because as you can see, depending on your predictor method, right, you're not necessarily going to predict right on the curve. And then we want to refine based on this to get back to our curve so that we stay close to our curve. And so generally the predictor method that we use is the classical RK4. That is in our software Bertini. I think that is the default that is used. And then for our corrector method, we use a maximum of 3 Newton iterations to just refine that. Because generally, as long as you have a stable polynomial system, 3 Newton iterations is plenty to be able to correct back to your path. And so now that we've found the solutions to f of z at p0, we can then use a parameter homotopy, a different type of homotopy, to solve this system at any other different values of p. So we can choose another p, maybe 2, 3, for example. And we can now deform from our f of z at p0 to f of z at p, which is 2, 3 here, but could be anything. And so the homotopy changes because now instead of moving from our natural start system of g of z to f of z at p0, we're now working with the same polynomial system, but we're just changing our parameter values. And so this is a linear homotopy in the parameters, where at t equals 1, the parameters are only defined by p at p0, p naught. And then as we move along the solution path, which will look the same as the previous picture, that we have these continuous paths moving between the solution points, it'll then move to the solutions at f of z at this new p2, 3, when we get to t equals 0. So we're moving the same way as we did before, but now it's just linear in terms of the parameters. And so why do we do this? So you're like, okay, now you have to do 2 homotopies instead of just doing the homotopy to the parameter points that you want. Well, the problem is that for these parametrized polynomial systems, if we think back to our computer vision example that I talked about way at the beginning, we're going to be given lots of parameter points for many different camera pictures, right? So we're going to want to solve it for a parameter point A, for a parameter point B, C, and so on. And sometimes this is like hundreds of thousands, et cetera, of parameter points that you want to solve for. And what happens is that when you do this initial solve with our g of z and our f of z at p0, what happens is that maybe you start out with 4 solutions, but the only non-singular isolated solutions to the system, f of z at p0, are 2. And so what we did with this initial step is we got rid of any paths that aren't going to impact our solution set at f of z at p0. Any solutions that go off to infinity any solutions that become singular. And what this does is that it creates the ability to only track the well-behaved paths, the non-singular isolated solutions for each different parameter value that we have. And these are much less costly. And so we can create a situation where we're able to solve much faster for these different parameters. So we do this once, and then we have the non-singular isolated solutions at f of z at p0. And then we're able to solve quickly for any other parameter point that we might care about for our polynomial system, for our example, which is something that we're going to want to do in many of these applications, right? Is not just be able to solve at one parameter value, but to be able to solve at many of them. And these paths might look different. So you might see the difference in the red, blue, and green paths, but ultimately we still get the same number of solutions when we move from P naught to P to some different P. Okay. And just to give a little background on how this number can change, because the difference between 4 and 2 is not that drastic. But when you have some of these more complicated polynomial systems, I've seen them go from like millions of paths defined by the Bézier bound to being just like 36, which is a huge difference, especially when the paths that are making up the difference between like 36 and 2 million are all singular or infinite paths. So the amount of time comparatively different between this single costly solve and then doing these smaller, faster parameter solves is huge. We did this one project that I'll talk about later where it took over a week to solve this initial one, and then it takes under a day to do each of these faster parameter solves. So it's very impactful when you're working with more complicated polynomial systems outside of this visual. Okay, so what we want to do is have stable systems, right? So it's very common for parameterized polynomial systems to be overdetermined. And what that would mean is that under a small perturbation, you're going to lose your solution, right? So if you perturb these equations just slightly, then you're going to lose your solution set. And why this is a problem is because if we can't find our solution, it leads to a situation where when we are using real data that comes from computers, cameras, other things in real world applications, the likelihood of us losing our solution if our system is overdetermined is very high. And so one of our first things that we're working with parameterized polynomial systems is we want to create a square system. And so let's just look at how we can do that, why that is possible. And so for overdetermined systems, since we're solving numerically, we want to use a technique called randomization to stabilize. And so this theorem in layman's terms, or well, mathematician layman's terms, I guess I don't know that I could go on the street and say this and people would understand. But what this says is that if we use a randomization matrix to define a new variety that creates a square system that then is numerically stable, the solution set is just going to possibly be a superset. So if we randomize, we're never going to get fewer solutions than our original variety and the original, overdetermined system. We just might get more. And so, but then you can always post-process after you solve for these solutions to then determine which of them belong to the initial polynomial system F versus this randomized, variety V of A times F. And so when we're using this randomization, we know that we won't we're not going to get any incorrect, or we're not going to miss any of the solutions that we want for our original system, which is very helpful. It's very strong. It means we can use these methods. And so let's just see, using an example, what this extra means, okay? And so the twisted cubic is a very famous overdetermined system in the algebraic community, algebraic geometry community. And when you randomize using some matrix A, where there's a little bit of structure here, right? We have the identity matrix and then a random vector to then be able to create a square system here. And what we get is, this is the twisted cubic in blue. And then we get this extra line that we, call this junk line, right? It's an extra set of solutions that solve this well-defined new system using the randomization matrix A. And so really the blue curve is all we want if we're trying to solve the polynomial system associated with F. And what we can do is we can just plug all of these solution points that define both the blue and the red curve into F and only save the ones that zero out F, right? Which would just be that blue curve, and we'd get rid of any solution points that are associated with the red line. And so while this isn't necessarily ideal, right, it makes the numerics stable and allows you to actually get the solutions to the curve, the blue curve, when you're using real noisy data rather than maybe not being able to find the solution at all. So I'd take some post-processing work over not being able to find the solution at all any day. And so let's go back to our 5-point problem and see how within this randomization using path data can impact our randomization technique and the effectiveness of our algorithm. So the 5-point problem here that I talked about before, so this is an image of various images that we can put together or that were taken of a 3D object. So this lion statue would be this like 3D object in space, and we could maybe stick 5, red dot stickies on the lion here. And then we take pictures of it. So in all of these pictures, we'd maybe see these 5 stickies, and those would show up as these xi and yi parameter points. And this is called a minimal problem because there's a finite number of solutions to the parameterized polynomial system that defines this problem. And that finite number is 10. And so the goal of the parameterized polynomial system here is to find this relationship matrix between the two cameras of the 2 pictures that you're taking data points for to solve. And once you have this relationship, there is then some equation that takes this essential matrix that defines that rotation translation and use this to then map back to the 3D object and determine its location. And the polynomial system for this problem is overdetermined. So we have the essential matrix is defined up to scale and projective space. We have these parameters, but we have 14 equations with 8 free variables. So this polynomial system that defines a very famous problem in computer vision is overdetermined. And so John and I, Jonathan Howenstein, my PhD advisor, worked together to develop randomization techniques that allow us to create a square, well-constrained system rather than having this overdetermined system, and apply these techniques to the 5-point problem. And we also did it for another problem, well, the 6-point problem in computer vision, which I won't talk about much here, but that just adds an extra parameter that talks about the any sort of distortion in the picture. So whether it has like a fishbowl appearance, that would be an extra parameter that defines that piece there. And so the question is how do we choose this randomization? And so the randomization matrix that we saw in the twisted cubic example was an example of a globally fixed choice. So we seemingly took a random matrix, although there was this structure. So it's not necessarily completely random, right? But we globally fix it. So we create this matrix right at the beginning. We multiply by our polynomial system, and that's our new polynomial system that we use for our homotopy continuation solving methods to find the solution. But another option is we can use the current path data. So if we remember back our homotopy continuation picture of these paths between solutions, we can use that local data along this path to make a new choice of our randomization along the path. So our randomization will no longer be fixed, but it'll be locally adaptive based on current data. And with the use of this current data, we use methods such as the singular value decomposition or something called leverage scores to be able to determine this randomization matrix. So those are the computations that yield the structure of this randomization matrix. Where the singular value decomposition is a dense matrix, and the leverage scores is actually a sparse matrix. So we take leverage scores and we essentially take the most, so leverage scores are based on a statistical computation that allows you to take like the most important equation that is most influential at that path point. And so our goal, right, is to take an efficient yet not computationally expensive choice, right? So we want to balance those things, which is always the hard part about numerics, right? Is you want to keep efficiency and accuracy, but not get too computationally expensive. And so without getting too much into the details of the singular value decomposition and leverage score randomization matrices, right, where you can consult the paper, we can talk later about more of the structure here if you'd like. But what I want us to look at is that if we just use the fixed, we take an average number of steps along this path for the 5-point problem of 14. That decreases using the singular value decomposition randomization matrix, which is again dense, to 10, 11. And then that decreases again to 9 when we use this leverage score method, which is a sparse matrix. So the impact of that sparsity actually helps us a lot, right? Because we are able to, our number of multiplications decreases. And so what we see here is that if we use, like the main point here, right, is that if we use local path data along our homotopy continuation path, when we're deforming from solutions at our start system to solutions at our final system, we see a decrease in about 35% in the average number of iterations when we use this local data. And so data can really have, or local data here along the homotopy continuation path can have a pretty significant impact on the efficiency and of the method when we're moving through the homotopy continuation path and trying to find the solution set. And again, the 5-point problem only has 10 solutions, right? So the impact here, while significant, right, is not necessarily like the largest that you could see. But for example, we have a problem that uses 3 cameras now, and they're called the Chicago and Cleveland problems that we have looked at. And there's Chicago and Cleveland because the number of solutions is, I think it's 312, and 264, if I'm remembering correctly. But the point is that those are the area codes for phone numbers in Chicago and Cleveland. So that was our, I guess you could say, creative choice of names for these problems. But essentially now, in terms of, instead of 2 cameras, we have 3, and we're still doing the same data point recognition. We have 3 points and 2 lines for the Chicago problem. And what we can do is use homotopy continuation here again. And there are 302, on the order of 300 and 200 solutions here. So if we use that randomization method, the locally adaptive one, we could potentially see a much larger impact because the polynomial system is more complicated and there are many more solutions. So in terms of the efficiency and speed of the algorithm, if we use this randomization method, it could have a much larger impact. But the situation here also with these 3 image problems, Chicago and Cleveland, there are many times where, again, we have difficulty due to lack of features, things that are correlated, so textures that are similar, so the matching features is hard to do. So picking out which points belong to which in each of the pictures, right? So here we can see, right, that pink, pink, pink and go together, but there's actually a computer software that matches these. And so if you have things that are too similar, it might match incorrectly, or you might get blurred information. And so using homotopy continuation techniques, we're able to solve a problem like this. So we have all of these, so I don't know if it's easy to see, but we have these red dots, which are actual data points that are picked out from the pictures. And we've highlighted these 3 in different colors that map to this structure here, right, where we have 3 points and lines. And this is the minimal problem with 312 solutions. And this is another example of an Amsterdam tea house data set. I'm not really sure exactly where that name came from, but it shows that our homotopy continuation methods not only work relatively closely to other methods, right? So the other method is in blue and ours is in red, and the ground truth, so the actual solution, is in green. And so we can see that our methods agree pretty consistently, right? There's not much difference here, and they're pretty close to ground truth, at least at the same point. But in this picture below, so the second image, the features are harder to recognize. And the other method, the Colmap method, is not actually able to solve the second set of images. Because of this first one, right? This dot here is pretty hidden or not easily found. And so the other method is not able to find a solution, whereas when we're able to use homotopy continuation mixed with these randomizations to help stabilize, we're able to find a solution. So that's a powerful piece here, right? We're able to find solutions where other current methods aren't. The drawback here is that our method is a little bit slower in the world of computer vision. So computer vision researchers really like to have things work in microseconds, which is not necessarily where our software lies. And so I think we got it to hundreds of milliseconds, which was pretty good for a homotopy continuation solver, but still not quite where the engineers theoretically would like the method to work. And so the other thing related to these projects is that, so we have this efficiency, we have the ability to use adaptive randomization to maybe speed up our computations, take a fewer number of steps. But we also don't care about the complex solutions, right? So this is something I mentioned earlier, is that we only care about real solutions when we're talking about these, with these real world application examples, right? And so is there any way to use the path data to not only create this randomization, but also to determine whether or not a solution is real, right? So what we are able to do is create kind of an end game termination process, and it's heuristic, so it's not, yeah, I'll just stop there. It's heuristic, right? But it uses this path data. So if this is our path, this describes the imaginary part of our path. So our path is defined by x of t, right? So we're moving from t equals 1 to t equals 0. So we're moving in this direction. And if at one path point we project, right, to the next one, and we look at the angle between this projection vector along this path, so the tangential vector, and then we take a vector from this point to 0, because, right, if our imaginary part of this path is, or if our solution on this path is going to end up real, this imaginary part is going to be 0. Right? And so this angle here, what we do heuristically is say, okay, with this angle value, is it possible, based on where we are in our t, to get back to a real solution, right? So here, this angle is large, or large comparatively for the situation. And we do this at about t equals 0.2 or 0.3, somewhere between 0.1 and 0.3. And what that does is it tells us, okay, well, we're close to our final solution set of our target system. And if this angle is larger than some value, I can't remember what we heuristically set it for the 5-point problem. But what we say is, if it's large enough, there's no chance in the little time that's left, or the little, path tracking interval that's left, for it to get back to having a 0 imaginary part, which would then make the solution real, right? So here we see that the solution ends at t equals 0 at an imaginary point, or having an imaginary component. But if we didn't have the rest of this curve, right, and we just had maybe these two data points, we can extrapolate here these two vectors, determine this angle between them, and then say, okay, this angle is too large. We're not going to get back to a 0 imaginary component at t equals 0. Whereas here, if we look at this other example path, right, or the imaginary part of that path, we can extrapolate these two vectors. Our angle between them is small, and so we say yes. The probability of it getting to a real, or a 0 imaginary component, so a real solution, is pretty high. And okay, so we use this path data. We say, okay, not going to be real, going to be real, and so what that allows us to do is, in this piece here, in this example on the left, we've tracked all the way to this point here. And then if we say that there's no chance it's going to possibly end at a real solution, we just stop tracking it, because we don't care about that solution. So why continue doing the work to find what the solution ends at? Because it's going to be complex, and we're going to get rid of it anyways. So we just stop tracking any solution that we, by this heuristic test at a non-zero t value along the path. We just terminate anything that is not going to possibly be real at the end. And this saves a lot of computation time and allows us to speed up our algorithm even more. And what we saw for our 5-point problem is that when we applied this method to only fixate on these real solution paths, we were able to decrease our average number of steps even more. So from 9 was our best before, using this adaptive data, local data for our randomization strategy, from 9 to 8. So there is an impact there, where again, I'd like to point out that, right, the 5-point problem is the simplest problem when it comes to these computer vision problems. And so if we extrapolate to something like the Cleveland or Chicago problem that I mentioned briefly earlier, the impact could be even greater. Whereas, so Chicago, I think, has on average, I think it's 40 real solutions, and there are 360 or 312 total. So the difference between that is pretty large, especially when you have a much more complicated polynomial system. So we can save a lot of computational time there. So in this vein of these real solutions, right, when you're doing a parameter homotopy, why even track the complex ones if you don't want them, right? So is there any way to only be able to track the real solutions from t=1 to t=0? So the previous piece, right, allowed us to use path data to truncate at t = maybe 0.3, but we still had to track these complex solutions, or possibly complex ones, right, from t=1 to t = 0.3, which is more than half of the interval, right? And so is there any way to just track the real solutions that end up at real solutions? And yes, there is. And so what we're able to do is create a picture of the complement of the discriminant locus. So the discriminant locus is a curve. You're not always able to find the equation of this curve explicitly, because it's the Grosvenor-Basie's methods, while they tell you 100% of the time that you are going to be able to get a solution when you plug it into something like Macaulay 2, it doesn't mean that it's going to terminate in your lifetime. I don't know if anybody's experienced that, but I think the usual heuristic is that if it doesn't terminate in like 45 minutes, then it's probably not going to terminate while you're alive. And so what we're able to do here is, so this picture is actually found using a machine learning algorithm, where we were able to provide data points in this region close to these boundaries and farther away. And the machine learning algorithm allowed us to find these boundary curves that differentiate between the number of real solutions. So this red section here has 0 real solutions. This orange section has 2. The yellow has 4, and the blue has 6, right? And it drops by 2 every time because we need, or adds by 2 every time because we need these complex conjugate pairs, right? So this describes the different, so the complement of the discriminant locus allows you to see sections in our parameter space. So this is defining our parameter values. So let's say we chose parameter value -1 and -1, we would get 0 real solutions choosing those 2 parameter values. And so if we want to solve for different parameter values, we know the regions of here, of, you know, this picture that allow us to track just from a set of real solutions to another set of real solutions. So for example, let's say at the base of this black line, we want to find the real solutions at this point, at the bottom of this black line. And we then say, because we determined a lot of data along this parameter space here, and for our machine learning algorithm, And so we've saved the real solutions at these points. And so you can have some, non-zero but non-extensive number of parameter values where you know the real solutions at those points. And then what we can do is we say we know the solutions here. We can just take the real solutions and track along this linear homotopy to the real solutions at this parameter point at the base. And for example, for the problem like the Chicago problem in computer vision, this path tracking here, you are now no longer tracking 312 paths, you're only tracking maybe 40 paths. For this example here, we're tracking, instead of 6 complex paths, we're only tracking 2 real paths. And so we found that this actually has a decent impact. So when we, and this is just for a small problem, so this is the Kuramoto model. And the classical homotopy, so that's tracking 6 complex solutions, took about 1.33 seconds. And so our number of paths is 2, so this is in that orange region with that black line that I just showed you. Our average time to track those 2 real paths instead of all 6 complex paths dropped to 0.077. So that's just the difference between 6 and 2. So if you could imagine the difference between 312 and maybe 40, right? That's like a huge difference. And our success rate was 100%. And why I mentioned this success rate is if we go back to this picture, you can see that maybe there's a situation where you'd have a real point here and you say, okay, what is the closest point that, that we have to track these real, the same number of real solutions, and you could cross over a different component of the complement of the discriminant locus, which would cause some singularity situations, which would disrupt the success of your ability to do that path tracking. Because what happens is that the solutions that become complex over this boundary, this first boundary on the right, might not be the same solutions that come out of this boundary. And so you're not necessarily going to get the solutions that you'd like to get. But as long as you sample dense enough, which I know that we could go down the rabbit hole of what it means to sample dense enough for different problems, different dimensional problems, but we're not going to do that today. But what we found is that if we have enough sample points in these regions, this purple line is not going to happen. And so if you use like a nearest neighbor method to find, this top parameter point, for example, this purple point will not happen. And for a higher dimensional problem, so the 4 oscillator Kuramoto model, we went from 3.4 seconds to under 0.15 seconds. So we still see a very good decrease in time, which allows for a much better efficiency when you only care about these real solutions. And the accuracy is similar. So accuracy, I mean the success rate. So the ability to avoid any of this crossing. Okay, so we've talked a little bit about how we can use path data to not only effectively randomize and get a better sense of, get a better description or, more effective solver, a faster solver, decrease computations, but also how we can increase that speed even more by only focusing on our real solutions, and again using that path data to give us that real solution component. But what we can also do is use a similar discriminant locus data set to determine behavior of solutions. So if we already have the solutions, we can determine how those solutions interact with each other. And specifically what I mean is how real solutions interchange. And so what that means is if we have so our parameters here, so this is a kinematic mechanism, so a parallel manipulator. And these pieces here are fixed to the ground. And these legs here are able to grow and shrink. And so they can move that top red triangle around. So the orientation of that triangle can change, but the triangle is fixed as well. So those side lengths don't change. So our parameters here are the leg lengths that can grow and shrink. But if you're given one leg length, there's a possibility that those same leg lengths can give different orientations of this red component here. And so the real solutions, how they interchange, is if we move around this mechanism from its starting leg lengths and move and change it and come back to that leg length, can we get a different orientation of this red triangle? And so this polynomial system isn't even the worst one that I've ever worked with, because it actually fits on a slide. I'm sure others can sympathize with this, right? So if we have this polynomial system, our leg lengths are defined by C here. So our variables are the P and phi here, and then our C is actually the square of the leg lengths, because working with square roots is no fun. And what we consider is we have our maximum number of non-singular real solutions is 6. And those 6 show up in these 6 mechanisms here. And so what this means is that all of these mechanisms have the same leg lengths. So all of these black bars in each of these 6 photos are all the same length. And so but we can see that the orientation of these triangles is different in each one. Okay, so we have 6 options, 6 real solutions at this parameter point. And if we take a real path in our real parameter space, can we change from this orientation to this one? And so what we see is that what these paths would look like. So if we start in this blue region and we take some path and we go la 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 la, we're taking a path here and we end up at the same parameter region, can we get a different orientation? So this is the region with 6 real solutions. We get another region with 4 outside of that, 2 in this bright blue, and then 0 outside. So again, a similar picture that we saw to the Kuromoto model before. And so an example of this path that I'm talking about, right, is, so we start with our 6 real solutions, we cross this boundary, take these real solutions here, and we end up at our same parameter values. And what we saw with this path is that by crossing these boundaries and going around these cuspidal points of our discriminant locus curve, we were able to move from one orientation of our mechanism to another. And you're like, okay, cool, I guess, maybe, but why does this matter? So for these mechanisms in kinematics, one example of when this might be useful is if this cannot happen, if your machine shuts down mid-path, you know exactly along the path of its job where it is, right? You know it's at task B, because if the leg lengths are such and such of this robotic arm, it must be at task B, because that's the only place it can have that orientation and those leg lengths. But if we have different orientations at the same leg lengths, we wouldn't necessarily know where along the path it is, because it has this ability to switch between the two. And so you would need to recalibrate your machine and start over. And so this has the ability to kind of give you that information. If you're able to perform this analysis on whatever machine you're working with, you would determine whether or not, in a power outage, for example, or if there was something that happened, whether you would need to recalibrate. And so hopefully over the course of this talk, you saw how for many applications that are able to be described by parameterized polynomial systems, not only are these parameter values data from real world places, such as leg lengths for kinematics, point data on camera images for computer vision. So data is involved as the input there, but that it also can be used within these homotopy continuation algorithms as input, such as data along the homotopy path to determine a randomization strategy and create stability, or to truncate any paths that aren't real, or being able to use discriminant locus information to be able to only track real solutions to real solutions, or determine the behavior of these real solutions and how they interact with each other. So there are many, many different ways that for even just homotopy continuation methods here, we can use data to find solutions and to increase performance of our various algorithms, where our main goal is to really only work with these real solutions. And so all these algorithms still involve complex computations because of the probability one situation. It's just a lot nicer to work over the complex numbers. But there's more work being done on how we can translate some of these classical algebraic or numerical algebraic methods from more complex behaviors to only focusing on these real solutions. And so finally, I just want to say thank you for listening. And if you have any questions or want to look at specifics of any of these pieces, they're all contained, details are all contained in these 4 papers. And then of course, you can send me an email or ask questions here, and I'm more than happy to discuss any of it with you. So thank you.